this video, we're going to extend our exploration of isomers, and in particular, we're going to look at the concept of enantiomers. So the focus here is an introduction to chem activity number 6. On the screen, you can see that we asked the central question, are molecules left or right-handed? Now, at first, you may not understand this question, but as we unpack these ideas, you'll see that it's quite a relevant question. Now, to begin with, though, I'd like to do a bit of review and connect to what we already know about isomers. So essentially, we're going to complete this chart again. We went through this exercise in chem activity number 5, but I think it's really important that you keep the context of the relationship of the different isomers. At the top of the teaching model number 1, I provide a table with a list of a bunch of different words and definitions. Well, let's take all those words and definitions and put them into this chart. So, of course, at the top of the chart, we have the word isomers. And, of course, isomers are different compounds with the same molecular formula. Now, there are different ways that this can happen. For instance, we can have structural isomers and we can have stereoisomers. Now, unfortunately, there's more than one way of saying this, so we call structural isomers also known as constitutional isomers. And stereoisomers are also known as configurational isomers. Structural isomers have a different attachment of atoms, and a great example is butane compared to methylpropane. Stereoisomers have the same molecular formula, but have a different arrangement in space. Now, we've met diastereomers, and today, in this video, we're going to see enantiomers. The diastereomers that we've met before are the EZ type. Those are those that involve the double bond. Now, as it turns out, there are other kinds of diastereomers. It's the EZ type that you're responsible for in this course. Because there are other kinds of diastereomers, a more general definition of diastereomer would be stereoisomers that are not enantiomers. The reason why this is a good definition is because enantiomers have a very specific definition. So any stereoisomer that's not an enantiomer must be a diastereomer. But as I say, you're only responsible for the EZ type for this course. Now, you may be a bit disappointed. I'm not going to share with you yet the definition of enantiomers. That's coming. I want to share with you, first of all, a story. Here's a news clip that comes from 2002. It has to do with a British skier that was stripped of his bronze Olympic medal. British skier Alan Baxter has been stripped of his Olympic bronze medal. The decision by the International Olympic Committee's Executive Committee was confirmed at a news conference on Thursday. Baxter, the first Briton ever to win an Olympic skiing medal, had failed the drugs test in Salt Lake City. You can imagine he was a very disappointed athlete. Well, let's find out a little bit more about this drug test. So what did the International Olympic Committee's drug analysis find? So here we have a chromatogram showing some banned substances, and we also have a chromatogram showing an analysis of Alan Baxter's urine. So as it turns out, Alan Baxter's urine contained the banned substance methamphetamine. Now, methamphetamine is also known as speed. Now, Alan Baxter claimed that he didn't use speed prior to his ski race. But in fact, he did use an over-the-counter decongestion inhaler, which he bought in Salt Lake City. Now, this decongestant inhaler is sold by Vicks, and according to Vicks, the active ingredient in the US Vicks inhaler is desoxyephedrine. This ingredient, in fact, has 3 variations in its somewhat common name. So one name is the levamethamphetamine, and then also you'll notice S-methamphetamine, and then finally desoxyephedrine. So you can see that indeed the Vicks inhaler contains methamphetamine. But the key here is that prefix S. So let's carry on. The compound methamphetamine exists as 2 chemical forms, or isomers. There's the S and there's the R. The S-methamphetamine has decongestant activity and no abuse potential. This is the active ingredient in the US Vicks inhaler. Whereas R-methamphetamine is the stimulant drug of abuse. Of course, this is not present in the US Vicks inhaler. Unfortunately for Alan Baxter, the analysis done by the International Olympic Committee's drug team was not able to distinguish between these two different isomers. Now, when you see their structures, perhaps you'll understand why it's hard to distinguish between them. Now, actually, these structures are shown in your course pack. On the left here, we have S-methamphetamine, the compound that's found in the Vicks decongestant. On the right, we have R-methamphetamine. Now, if I draw a line here and then indicate mirror, perhaps it's quite clear to you that these are indeed mirror images. They have the same atom connectivity, but they have a different arrangement in space. As it turns out, therefore, they are different molecules, but they are related by the fact that they are mirror images. Now, this brings us to our definition of enantiomers. These compounds are specific examples of stereoisomers that we call enantiomers, and enantiomers are non-superposable mirror images. So while they are mirror images, they're not identical. Now, to help you see how this works, I've built some models, but rather than make models of the entire structure, including the benzene ring, what I'm going to do is I'm going to use a blue ball to represent the nitrogen and a red ball to represent the CH2 benzene ring. I'll use a black ball just to represent the CH3 and a white ball to represent the hydrogen. So here we have our models. And like I say, I've got the blue for nitrogen, the red for the CH2 benzene. You can see the white ball representing the hydrogen and the black ball representing the methyl group. Now I've lined them up so that you can indeed see that they're mirror images. But what I'd like to point out to you is, if I now try to superpose them, that is, put one on top of another, and so first of all, I'm going to put the black ball on top of the black ball and the white ball on top of the white ball, you can see that the red and the blue don't line up. And no matter how we rearrange them, so for instance, if I now take this and rearrange such that the red and the blue line up, well, then you can see that the black and the white don't line up. So once again, they're mirror images, but they are non-identical. We know they're non-identical because they're not superposable. Now, one of the things that you might be wondering then is it true that all mirror images, that is, all molecules that are mirror images, are all of them going to be enantiomers? And the answer is no. To give you an example, let's just look a little further in the course pack, where I've drawn a modification of the methamphetamine molecule. I've simply taken off the methyl group and replaced it with a hydrogen. So here you can see that indeed these are mirror images, but the question is, are they enantiomers? And so let's turn again to our models. Here you can see I have the blue ball that represents the nitrogen, the red ball that represents the CH2, CH3. But now I have two white balls representing the two hydrogens. When I put one molecule on top of another, you can see that they're perfectly superposable. So therefore, not all mirror images are enantiomers. And so they're just going back to the notes then, these are not enantiomers. Rather, they're superposable mirror images. Now, what does that mean to say a superposable mirror image? Well, it means it's an identical molecule. So you might be wondering, how the heck are you going to decide whether or not a molecule has a mirror image that's non-identical? That is, how are you going to decide whether or not a molecule has an enantiomer? It is actually quite easy. There's something characteristic about one of the atoms in methamphetamine that allows us to know that it would have an enantiomer. So in the box that's in the middle of page 32 of your activity, you have an opportunity of one, writing down the definition of an enantiomer, non-superposable mirror images, but also you have an opportunity of defining what we mean by chiral and a chiral carbon. So I've given you enough room to do this. So let's unpack these ideas a bit. Now we say that a molecule that has an enantiomer is chiral. And that comes from the Greek word care, meaning hand or handedness. Now, a chiral molecule can be identified by finding a chiral carbon. In other words, if a molecule has one chiral carbon, that molecule will be chiral. That molecule will have a non-superposable mirror image. How do we find a chiral carbon? And a chiral carbon is also known as an asymmetrical carbon. It's simply finding a carbon that has 4 different groups attached to it. So here, once again, is our S-methamphetamine. And if you take a look at this carbon, about which we've drawn the wedge and dashes, you'll notice it has a nitrogen as part of an amine group. It has a CH3, it has a hydrogen, and it has a CH2 benzene ring. So it's true, it has 2 carbons, but these carbons are not identical. One is in the form of a methyl group, and the other is in the form of a CH2 benzene ring. So there are 4 different groups attached to that carbon. This carbon is therefore chiral. The molecule, therefore, is chiral. The molecule will therefore have a non-superposable mirror image. In our synchronous sessions, we'll explore how to identify chiral carbons in molecules. We'll also explore how to designate which particular enantiomer we're working with. In other words, whether or not an enantiomer is the R isomer or the S isomer.